In this chapter, we will be dealing with some thermal properties of materials. We'll also be looking at some of the concepts associated with heat flow and the types of heat transfer mechanisms. Some properties that you think about that are associated with the thermal aspects of a material are such as things as expansion and contraction, thermal expansion and contraction, properties that relate to the electrical aspects of a material that's subjected to temperature changes that will cause current to flow. Optical properties, the color of something that changes according to temperature. Simply the temperature change, how a material responds to heat energy, is a thermal property. Structural rearrangement, phase transitions, different types of phases in materials as a result of temperature and the way heat is utilized by that substance and the way that the temperature of the material is changed, such as in the process of heat treating and quenching, getting different phases of steel, martensitic, austenitic phases, are all structural rearrangements as a result of temperature and thermal properties. The response to heat energy. What happens when you add heat to water? Well, if you think about it, if you add heat to water, what are the consequences of that? Well, imagine doing this kind of experiment. Start with a kilogram of water at 10 degrees Celsius. And notice here on the graph, we're going to plot the heat that's put in. And we know that heat energy is in joules. And as we add heat energy, we notice that the temperature rises. So we have this linear plot as the temperature rises. Okay? If the mass doubles, the temperature will only rise half as far as it did in case of having 1 kilogram at 10 degrees Celsius. If I have 2 kilograms at 10 degrees Celsius and I add the same amount of heat to it, I'm only going to see a temperature increase half as much. So that tells you that then that the heat, you can remember the graph is a linear graph, the heat put in is directly linearly related to the temperature of the substance, temperature change. If we double the amount of heat flow, we'll double the temperature increase. So all of these observations can be encompassed in an expression as follows. It says Q, where Q is the heat, it's our symbol for heat, is the mass of the substance times the temperature change it undergoes times a quantity here. You'll notice this little c here, proportionality constant, which is a characteristic of the material. If we were to rearrange this equation and say Q divided by m delta T equals C, we would find that the ratio Q over m delta T is always a constant for a single material. In other words, if I double the amount of heat Q that I put in, the temperature will double as long as the mass stays constant. The ratio Q over m delta T will stay constant. If I change the mass, I double the mass, okay, the mass was in the denominator, and I keep Q equal to the same, the temperature will only increase by half as much, but the ratio Q over m delta T will still be constant. And so we're going to find that this C value, this proportionality constant between the heat Q and the product m delta T, is a material property that's known as the specific heat. The specific heat is a ratio of the heat needed to raise a kilogram of material by 1 degree Celsius. Notice here C is a ratio of Q over m delta T, where the units of C are in joules per kilogram degrees Celsius. It may be in joules per gram as well. You just have to look at the tables that are in your book to see how they're expressed for particular problems. Notice we have some examples here. Water, and I see there should be a comma here. There should be 4,184 joules per kilogram. There's 920 joules per kilogram if we're dealing with aluminum. So each material has its own respective specific heat, which is a representation of the fact that the materials are composed of different elemental structures, water being H2O, a molecular structure. In the case of liquid water, having 4,184 joules per kilogram specific heat. That structure is much different than the structure of aluminum, and therefore it's reflected in the fact that it's not 4,184 for aluminum, but it's 920. So this is a material property. It tells us something about the structure of that material. If we can measure this material property, we can identify the material because it is part of its unique fingerprint. Let's compare the temperature needed to raise the same mass of water and aluminum by 40 degrees. Now, this question gets at the nature of what we're talking about here is specific heat. What is the specific heat telling you? If you think back on the number for water, it's 4,184 joules per kilogram per degree Celsius. So let's separate that a little bit here. That's 4,184 joules for 1 kilogram to go up 1 degree Celsius. Then contrast that with aluminum. If we want to take 1 kilogram of aluminum up by 1 degree Celsius, we only need to add 920 joules of heat. So it takes less heat for the same amount of material to go up the same temperature for aluminum versus water. Okay? So here, compare that needed to raise water by 40 degrees as compared to aluminum. So it's obviously going to take more, isn't it? Each kilogram of water is going to require more heat to raise it by 1 degree than the aluminum. So it's not going to be this one, 4.5 times more for aluminum. No, it's not going to be the same because we know the specific heats are not the same. And water's not going to be less. So it's got to be 4.55 times more for water. So as you look at the numbers for specific heats for various substances, just remember that as you're looking at them, what it's telling you. It's telling you how much heat do I need to raise this quantity of material by a specified amount of temperature. Now, as you add heat to substances, and as we saw in the previous slides, the temperature increases. Obviously, you're going to get to some point. For instance, if we use water as our example, some point when the liquid water is increasing in temperature, we know that if we continue to add heat, we're going to vaporize that water. It's going to turn into the gas state. The states of matter are solid, liquid, gas, and plasma. We're only going to be concerned about the first 3 typical phases of matter that we deal with in everyday life. We know that as a result of the addition of heat, we're going to reach a point where we can change substance's phase. Either a solid, such as ice, by adding heat can be melted to become a liquid, or vaporized by adding heat to become a gas. So there are lots of different things that we need to look at with respect to the phases of matter and characteristics of each one of these phases, such as in the gas phase, pressure, volume, and temperature, etc. We know that, for instance, as I mentioned before, water is solid at 0 degrees or below at standard pressure. We know that it's liquid between 0 and 100, and at 100 or above, it is gaseous. So let's plot temperature versus heat energy for water throughout a regime that will encompass all 3 of these phases. In this graph, you can see that we are starting with water down here in an ice state, actually below zero. In other words, even though there's no number shown on this graph, right here on the temperature axis would be 0 degrees Celsius. And right about here would be 100 degrees Celsius. So what we're representing here is ice at some negative value of temperature, such as -10. Now as you add heat energy, Q, notice that we're plotting here along this axis, Q. So as you add heat energy to this solid ice, which is at negative temperature, you're going to raise the temperature of that ice on a linear relationship here. Well, anytime you have a linear relationship like that, we can apply the formula Q equals mc delta T, because that's showing us that Q is linearly related to the temperature change delta T. And the specific heat of ice will be a value different from the specific heat of liquid water. It's roughly half that. So the slope of this line is actually the value of that specific heat. Notice a little more gentle slope here versus over here a little steeper slope. So what's happening in the first segment is the solid is warming up, but it's still a solid. Now notice then we get to this plateau region, and we continue to add heat energy, but the temperature is not increasing. What's happening there is the phase is changing from solid to liquid. So in the first portion here we have a solid. In the second portion we have sort of a mixed phase going from solid to liquid as the solid melts. It stays at a constant temperature of 0 degrees Celsius, which is in this case the melting point of the ice, until all the ice is melted, and then as we've continued to add heat, now it's liquid in this state here, and we're rising in temperature up to 100 degrees Celsius, where once again we have a mixed state, a second plateau, where the liquid and the gas phase, the liquid is transforming into the gas phase, we have a mixture, and as we add heat energy we vaporize the entire liquid sample, and then finally the whole sample is able then to increase in temperature as we see in the last sloping portion of this graph. Okay? So we have yellow regions here represent regions in which the phases are constant, solid, liquid, and gas. And then we have the plateau regions in which the phases are changing. Now we cannot use Q equals mc delta T on these two plateau regions because notice, even though Q is increasing, T is constant. And using Q equals mc delta T would give us Q equals 0. So that can't be consistent. So we have to have a different way of expressing the amount of energy added in this portion here where Q is increasing but T is not increasing. And those places where the phase is changing, plateau regions there, are described by Q equals mL. In other words, the amount of heat that's necessary to take that mass m to another phase, to a different phase from the one it was in, is given by the product of m times L, where L is the latent heat of that substance. And we have two latent heats to deal with. One is the latent heat associated with melting, which is called the latent heat of fusion, and one which is associated with the latent heat change, the phase change going from liquid to gas, which is the latent heat of vaporization. So the value of L here will be either subscripted F for latent heat of fusion or V for latent heat of vaporization. If you think about it, if the question were asked, if I had a kilogram of water or ice here at minus 10 degrees, and you were asked, how much heat would I need to add to take that kilogram of ice all the way to the other end of this graph, which we'll say is at 110 degrees Celsius, meaning it's gas. How much heat would I have to add? Well, notice there are 5 steps. There's a step where we have to warm up the ice, melt the ice, warm the water, vaporize the water, and warm the steam. 5 different calculations. The 3 calculations that involve the sloping lines will use MC delta T. Now, C is going to be the C that's corresponding to the particular phase, whether it's solid, liquid, or gas. The phase, the amount of heats for the transition points between solid, liquid, and gas, we're going to use Q equals M times L, where again, L is the latent heat of fusion or vaporization. Here we have latent heat of fusion for water is stated at 335 joules per gram. Okay. And the latent heat of vaporization is 2,260 joules per gram. Notice there's quite a bit more energy needed to convert the liquid to vapor than there was to convert the solid to liquid. For that reason, that means that the steam actually holds much more energy than the liquid. In other words, you know that steam is at 100 degrees or higher, and certainly that would be a painful temperature at 212 or higher Fahrenheit. But the really critical part about it is that as that steam is actually has a capacity to hold much more heat. And so if you imagine the steam getting in contact with your skin and then condensing to a liquid, it has to liberate that excess heat, which is the latent heat. So that excess heat is significant and causes severe burns. As I mentioned before, you might imagine doing this problem, how much heat is needed to take a kilogram of ice at minus 10 degrees Celsius, and take it up to 110 degree steam. So calculate each one of these steps using Q equals MC delta T, Q equals ML, Q equals MC delta T, Q equals ML, and finally Q equals MC delta T. You might want to write down these numbers or pause the recording at this point so that you can do this problem. Now, in this chapter, we're looking at some thermal properties, and so that leads us also to observations of how heat is transferred from point to point, what kind of mechanisms are involved. We have 3 primary mechanisms: heat conduction, heat convection, and radiation. What differentiates these 3 types of mechanisms is as follows. One requires that you be in contact with the source of heat, and that's heat conduction. One requires that there be a medium that transfers heat energy from the source to the desired place, that's convection. And the last one is radiation, which requires that there be no contact between the source and the desired location for the heat, but it is simply transmitted by electromagnetic energy. Let's look at them individually. Heat conduction. Here we have a representation of 2 regions of temperature T1 and T2 separated by a boundary by a layer of thickness L. This area A is representative of the cross-sectional area of this thickness L. Imagine a piece of glass between the inside and outside of in your house. So the window has a certain area, has a certain thickness. It's comprised of a material that we can characterize by thermal conductivity. Again, that's a material property, just like specific heat would be a material property or density. You can imagine then, if you go through sort of a mental exercise here and say, under what circumstances would the heat energy flowing from the inside of your house to the outside change. In other words, let's imagine a warm house, cold winter day. So heat's going to flow from hot to cold, from in to out. Okay? What's going to have a greater heat flow? A large window or a small window? Of course, you answer a large window, right? So that means if the heat flow is greater for a large window, a large area, then that is a relationship that says the rate of heat must be directly related to the area, right? Q is related to A. How about the thickness? Would a thick window versus a thin window, would a thick window have more heat flow or less heat flow? And you're thinking, and you say less heat flow. The thicker the window, and the more the insulating. So since L characterizes the thickness, then if that's big, we want that in the denominator because Q will be smaller if L is bigger. Okay? Well, how about the temperature? If there is a small temperature difference between inside and outside, then there's not really much driving force influence for that heat energy. But if there's a large temperature difference, there is a greater tendency for heat flow. So that means that the heat is directly related to the temperature difference between the inside and the outside. Okay? So I just wanted to give you some idea as to why those terms fall where they do in this expression. So you notice that the rate at which heat flows, which is the joules per second, is a watt, isn't it? Joules per second. So the watts of heat flow are the material, constant thermal conductivity, area, the temperature difference, and then the thickness. Okay? That's a pretty straightforward equation. Heat convection requires that there be a medium, such as in forced air. The air is the medium which moves, goes from the furnace, is warmed up, and then that heat is then taken into the room and deposited there. So that's the medium. You can also think of the convection of heat on the stove in a pot of water. The vegetable placed in a pot of water is cooked by the fact that the water is heated at the base, bottom of the pot. The water rises, convecting that heat energy into the vegetables, cools and falls back down, and is heated again. So you have a convective cycle there, a convection cell going on. In the previous slide, when we dealt with conduction, there was contact between the two temperature regimes, T1 and T2. In this case, there's no contact between where the heat is generated, such as the furnace, and where it is deposited, such as in the room. Now, that means that the shape of the room, the shape of the ducting, the windows present in the room, all sorts of different factors will come into play in trying to figure out the exact heat convection formula to use. And that's much more complex than we want to deal with. So we'll just simply say that that's one of our types of heat transfer, but it's a complex fluid dynamics problem. So you won't have a formula for that one. Okay? Now, the last form of heat transfer is known as radiation. Remember that the word radiation only means that it's energy in the form of electromagnetic radiation. Can span, electromagnetic radiation spectrum spans all the way from very high energy, gamma rays, as we come down through the microwaves, down into visible, down below to ultra infrared, and so on, radio waves, and so on. So from high energy to low energy, that's the spectrum of electromagnetic radiation. Energy transmitted by electromagnetic radiation, then, is a result of the fact that the object has a temperature. And the law, known as Stefan's law, tells us that the power of the energy transmitted, in watts, of course, power is joules per second, is proportional to the area of the object that is radiating that energy. It's proportional to the fourth power of the temperature in Kelvin of that object radiating energy. There is a constant E here called the emissivity, which is characteristic of the color of that object, where very, very light objects, like white objects, have essentially low emissivity, 0 value, and very dark objects have a value of close to 1. So from 0 to 1 is typical range for E. And then sigma is known as the Stefan-Boltzmann constant given down here. Now, very important, the area has to be expressed in square meters, because notice that the Stefan-Boltzmann constant has a square meter unit, and it has to be expressed in Kelvin temperature, because Kelvin is in that constant as well. So you can imagine that then if we know the amount of, say, radiation being received here on the Earth from a star or sun, then knowing the amount of power being received and knowing the area it's being received on, we can work backwards to determine what is the temperature of that object that is radiating that heat energy. So it's a very interesting expression. Okay.